and glass makers pioneered a unique and ingenious way to manufacture the glass fiber.
Right, it's optical fiber there.
At that time,
some people get really into the video and I don't want to disrupt them if they're really enjoying it, so. All right. Well, good afternoon. As some of you know, my name is Jen and welcome to the optical fiber demo. What I'd like to do for you today is answer some just basic questions that most people have about fiber optics. What is it? How does it work? And what does it do for us? Well, this is a sample of optical fiber. It's a thin thread of glass, barely thicker than a human hair, through which we can communicate information like our telephone calls, our internet signals, and even our cable TV service. Now we send this information in the form of light. So a computer creates a code of ones and zeros out of all of our information. And that ones and zeros code is then translated into ons and offs of a laser beam that is sent down the length of the fiber to our devices, to our phones, TVs, and computers. Now light has a couple of interesting characteristics which help us out with this. And one of those is that regular old white light can be divided into many wavelengths. So you can see here the 7 wavelengths we can see with the human eye, but there are hundreds more wavelengths that we can't see. And we can send our information on almost all of these different wavelengths. They're sort of like different channels on your television.
More on the camera.
Now the other thing is that these wavelengths don't interfere with each other. So we can send different signals on all the different wavelengths all at the same time. The last thing is light is just incredibly fast. So given all of those factors, this thin thread of optical fiber can handle more than 500,000 phone calls all at the same time. Now prior to optical fiber, and in some places today, like me, you live out in the country, we had copper wire networks, or coax, and that's a sample of it over there. And with copper, we sent our information in electrical signals. Now, unlike light signals, the electrical signals would interfere with each other, and then you lose your information. So basically, we can only do one signal per wire. Also, electricity is just really slow compared to light. So to handle the same amount of information as this thin thread of glass, it would take that entire 6-foot bundle of copper wire on the wall over there to do the same job. So just in sheer mass, you can see what a great advantage this is. Now, I keep mentioning we're sending information in the form of light, and that may sound like something out of Star Trek, but it's really nothing new. We've been communicating with light in very simple ways for many, many years. But how do we do so accurately today? I mean, how do we even get it to stay in there? It's a clear strand of glass. Wouldn't it just leak out the side? Well, to handle that problem, we're actually going to look at an innate characteristic that the glass already has, which is total internal reflection. Now, this looks really complicated, and I promise in a couple minutes you're going to understand this. Basically, light travels different speeds through different materials. So you've heard of the speed of light. That's pretty basic. It's how fast light travels in outer space. But light travels much more slowly in water and even more slowly in glass. Now, we would think this would work against us because don't most things want to travel the path of least resistance? So things are easier and faster? Well, light seems to be a glutton for punishment, and it likes to move more slowly. So once it is trapped in a material like water or glass, it will tend to stay there due to this internal reflection. Now I have some experiments to show you that should illuminate this a little better. We have 2 water tanks here and a slide projector. The slide projector is focusing a thin beam of light through the upper tank and out the spigot. So when I turn the spigot on, hopefully the water is going to come out. That's the first thing. But what's the light going to do? Where's that going to go? Let's take a look. Well, the water's doing what it's supposed to do, which is a good thing. But where's the light? The light is trapped within the stream of the water. It's taking the path of greater resistance. So I can prove this to you by disrupting the flow of the water with this board, and you can see it light right up with that light that's in there. But as soon as I take the board away, the light continues to follow the path of the water. Now this is not a new experiment. This was actually first done in like the 1840s by a Swiss scientist named Daniel Paladin. And he was way ahead of his time because this is the fundamental basics of how fiber optics works. The only thing they had the ability to do back then was light up some really cool fountains in Paris. took another 100 years for us to have all the other pieces of technology to start making use of this. Now I have 2 more experiments here with our laser beam. And I'm going to shut this off, but don't forget this because we're going to come back to this. I saw that. Love it when people get my references. So, laser's going from one end to the other in a straight line, just like it's supposed to. But what's going to happen when I try to aim that laser upward and get it to break the surface of the water and go up to the ceiling? Let's take a look. It's not going to leave the water. So again, it's moving slowly in the water. It hits that interface between the air and the water where it's suddenly going to have to start moving more quickly. And that creates kind of a mirror effect and sends that light back down. Now I don't know if you've ever gone swimming underwater and then you look up while you're underwater and instead of just seeing the clouds in the sky, you actually see what's around you underwater reflected in the surface. And it's the same thing. Light's going up, hitting the interface between the air and the water, and it's sending that light back down. Now, I told you this all would make sense in a minute. I'm going to make this slightly steeper. Not too steep, because if it's too steep, this will stop working. That's one of the parts of this. Now, this is known as refractive index, if you've ever heard that term. This combination of how fast the light travels and the angle at which it's hitting that interface. So, here's our water, here's the air, and here's the laser beam. And all that math is saying is that the light needs to travel more slowly here than here or here. That's all that's saying. So, it's not quite as complicated. Now, while this is really cool, though, we don't make our optical fiber out of water. We make it out of glass, right? So let's take a look and see what happens when we move this over to the glass. And if you'll give me a moment, I've got to change the channel because I have this nice setup here. We have the laser going into this block of lead crystal, and then there's a camera pointed down the end of the glass towards the laser. So we're going to get a real good view of the inside of this piece of glass. So as I move this laser around, look at it reflecting off of all of those internal surfaces. It kind of makes this thing into a hall of mirrors. And again, the light is forced to move more slowly in the glass, so that interface between the air and the glass is creating that mirrored effect, keeping the light in. Now let's try the same experiment. We're going to aim that laser beam upward, try to get it to break the surface of the glass. And you can see very clearly that it's reflecting back into the glass. Now the cool thing about this is, that's what happens when you make a phone call or do a Google search. Your information's translated into a laser beam, then sent down the length of glass to your device. So it's pretty cool that we can actually see a version of it here happening live. Let's turn this off and get the TV back. Now I'm sure you're all burning with the next question, right? But what kind of glass can we use? That would be my next question. Can you use any glass, like window glass or bottle glass? Does it matter? Well, it does matter. Now, all glass will have this property of internal reflection, but some glass actually transmits light way better than other kinds of glass. We measure this on a scale known as optical purity. So I have 2 samples here to show you on opposite ends of the scale. On the low end of the scale is soda lime glass. Your windows, drinking glasses, pickle jars, light bulbs, windows, all made out of this kind of glass. We think of it as clear. I mean, I can look out now and see that the sun's going down a little bit. But if you've ever looked through a significant thickness of this glass, you'll notice it's not actually clear at all. It's kind of greenish colored. That's because the ingredients that make up glass include iron. And those iron particles are getting in the way of the light. So the thicker the glass, the more particles of iron. At a thickness of about 3 to 5 feet, this thing's opaque and you can't see through it at all. That's fine for the window, but if you're trying to communicate to the other side of the world using light through glass, 3 to 5 feet is just not practical. Lucky for us, right here in Corning, New York, scientists discovered a new kind of glass. This is high purity fused silica. It's made in a laboratory, and it is so pure and so clear that we can send information in the form of light up to 125 miles at a time before it needs to be re-amplified. So that's getting a lot better. So 3 to 5 feet or 125 miles. I think it's pretty clear what the better option is here. Now, it was that invention of that high purity fused silica here in Corning, plus the invention of the laser beam in the 1960, all the way back to Daniel Collins' original work in the 1840s, that we now have all of the pieces that we can start doing fiber optic networks. Now, I keep stressing how clear this glass is, and that certainly is a very important part. But it has another trait that might surprise you. I told you this is really strong stuff. This is my least favorite part of the show because it kind of hurts. I can try to pull on this and I'm not going to break it. The stuff is really tough. Now, glass typically will break when you're pulling on it in a weak spot, where there's a scratch or where there's an imperfection or impurity in the glass. This glass is so pure and its surface is so pristine, there simply is nowhere for it to break, and so it just really doesn't. That doesn't make sense, right? I mean, you drop a glass on the floor and it breaks, and we always think of glass as fragile, but we always think of steel as strong. We have a superhero named Man of Steel. We do not have a superhero named Man of Glass. But maybe we should start. I think we've got a trend here, because if we look at a tensile or pulling strength comparison, optical fiber is 3 times stronger than steel and 4 times stronger than those copper wires they're replacing. It's not too shabby for a little thread of glass. Now, I keep saying thread of glass. It's slightly more complicated than that, but not much, I promise. Each piece of optical fiber, which is including this one here, is actually made of 3 distinct layers. The inner layer is the core. That is this high purity fused silica that's been doped with a couple extra ingredients to slow the light down through it. Now, surrounding that is the cladding. Now, the cladding is made of that same high purity fused silica minus those couple of ingredients. And so the light's going to travel more slowly in here, and the interface between those 2 types of glass work just like these 2 examples to create that mirror effect and keep that light in the middle. And so all of our information stays in the core and we don't lose it. Now, this stuff is really strong, but if it gets scratched, it's going to break. And so we add this outer coating of plastic just to keep the integrity of the surface intact. So now you know what it is and you know how it works, but what do we need it for? What does it do for us? Well, that can be summed up in one word, which is bandwidth. Now, bandwidth is just a measurement of how much information you can put in your network at a given time. That's all it is. And I have a sample here to show you, and I will apologize to the people in the way back. You may not see much of a difference. So I will leave this up, and if you want to come up and check it out, the farther you are away, the closer these 2 sides look. So this is an HD TV. And on this side is what it's supposed to look like. It's clear, it's crisp, you see all the details, and when things move you can see the details. This is often what we get at home. We get this fuzzy distortion or kind of a blocky effect, especially here, known as tiling. Now, there's nothing wrong with the TV, so unless you are hoping to get a bigger one out of the deal, don't go home and throw your television away. What's happening here is your TV is not receiving the information fast enough to complete this highly complex picture. And the reason that's happening is because somewhere in the network between your provider and your home are probably those copper wire cables slowing down the signal. Now, we already talked about how copper is just inherently way slower and limited than optical fiber. So there's nothing left to do except replace it. So that is what's happening. Any new construction is all being put in with optical fiber, including within the house itself. And as the companies are having to repair these old copper wire networks, they're often just replacing them with optical fiber. As that happens, our cell phone calls and regular phone calls are going to be more clear and consistent.